Math 2414, series, video 5, repeating decimals as geometric series. In the last video, as I was deleting and getting ready for this one, I realized I misspelled geometric. I spelled it geometric, which I guess is a redneck way of saying geometric. But that's okay. I'm cool with that. But sorry for the typo. But anyway, I mentioned in the first video in the series that you've seen infinite series before as repeating decimals. And just to remind you how to get a decimal from a fraction, it's really just a division problem. This goes back to elementary school. For example, let's say that you had, what's a good decimal? Let's say you had 7/12 and you wanted to represent that as a decimal. Well, every fraction is just a division problem. So you would go out to the side and start doing 7 divided by 12. Bringing in the decimal and zeros is necessary. 12 goes into 75 times. 5 times 12 is 60. 70 minus 60 is 10. Extra 0, bring it down. 12 goes into 100. Let's see. Looks like it's going to be 8 times. 8 times 12 is 96. 96 from 100 is 4. Bring down a 0. 12 goes into 40 3 times. 3 times 12 is 36. And then once you get the same difference in your subtraction part, that's when the decimals will start repeating. So we're going to get that. We're going to get 0.583. So ever since you've known about fractions and decimals and division, you've been able to convert fractions to decimals. Now, you should have been taught a way to convert repeating decimals back into fractions. Finite decimals, those are easy. And there is an algorithm, if you will, for converting a repeating decimal back into a fraction. In other words, if you started here, how would you turn it into that? But in light of what we know about geometric series, we can now use that approach to convert any repeating decimal back into its fraction equivalent. So we're going to do that with this one. Right, 2.317171717 as a ratio of integers. Now, there's a couple of ways to do this. One is to view the decimal as a sum of powers of a sum of reciprocals of powers of 10. In other words, 2 plus 3/10 plus 1 100th plus 7 1,000th, et cetera, and look at each decimal individually. And another way is to look at the repeating block as a single entity. In other words, don't look at that as a 1 and as a 7, but look at it as a 17. I'm going to choose to take the single digit approach, and let's see how that goes. We have 2 plus 3/10 plus 1 100th plus 7 1,000ths plus 1 10,000ths plus 7 100,000ths. Now at this point, we might want to start using powers of 10. I don't know why I put a comma there. And in fact, I think I want to do that. I think I want to rewrite all the denominators as powers of 10 just for convenience. So let's get rid of all these and replace them with their corresponding powers of 10. All right, so we got 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth, 1 over 10 to the sixth. Let's tack on one more. Plus 7 over 10 to the seventh. All right, so if you'll notice the 1 and the 7, the fractions of 1s and 7s, we could form a geometric series out of those. The two guys in the front, the 2 and the 3/10, I'm not worried about that. Let's rearrange these. Now, there are criteria under which you can rearrange an infinite series and preserve the sum. There are some instances where you can rearrange an infinite series and it changes the sum. We're not going to go that into depth. Let's just assume that we can rearrange the terms of the series. So we have this 2 plus 3/10 sitting in front doing nothing. Let's gather everything with a 1 on top. 1 over 10 squared, 1 over 10 to the fourth, 1 over 10 to the sixth, dot, dot, dot. And let's gather everything with a 7 on top. 7 over 10 cubed plus 7 over 10 to the 5th plus 7 over 10 to the 7th. Okay. We have two geometric series. The first parentheses is a geometric series where the ratio is 1 over 10 squared, because the power on the exponent on the 10 is going up by 2 each time. What's the first term? The first term in this series is right there. In the other one, the first term is 7 over 10 cubed. Well, what's the ratio? It's also 1 over 10 squared, because as we go from term to term, the denominator's power is going up by 2. Both of these ratios have absolute values that are less than 1. Each ratio is equal to 1 over 1. That means that as an infinite geometric series, both infinite series in parentheses converge. And now we simply have to see what it converges to and then add everything up. Let's clean this up and then we'll continue. All right, so we have 2 plus 3/10 plus, for the first series that starts with 1 over 10 squared, the first term is 1 over 10 squared. So the first term is 1 over 100. The ratio is 1 over 100 as well. For the second part, the first term is 7 over 10 cubed, so it's 7 over 1,000. Got a little bit better. Gotta make it better than that. 7 over 1,000. And the denominator is 1 minus the ratio, which is also 1 over 1 minus 100. All right, so let's start cleaning this up. In both denominators, 1 minus 100 is 99 over 100. Let's write that. Good. 9 over 100. Now we have two complex fractions, one fraction over another. But anytime you have one fraction over another, you could multiply both. You can multiply the top times the reciprocal of the bottom, or a strategy that will always work, regardless of how many fractions are on both sides, is to multiply both sides of the fraction by the least common denominator of the little fractions. For the first fraction, both denominators are 100. But in the second fraction, the least common denominator is 1,000. Multiplying by 1,000 will give us enough ammunition to cross out all of the little fractions. In the first one, the 100s cancel on both sides, and that's going to leave 1 over 99. So let's clean that up into 1 over 99. Big mess here. Comes 1 over 99. And in the second one, the thousands cancel here, but this 100 would go into that 1,000 10 times. So the denominator here would be 99 times 10, or 990, with a numerator of 7. So the second one converges to 7 over 990. Let's clean that up and write 7 over 990. Okay, so now we have to do is figure out what these fractions add up to. Looking across the denominators, 990, 99, 10, and 1, it looks like the least common denominator of all four fractions is going to be 990. So we need all of these to have a denominator of 990. We'll multiply this fraction by 10 to get the 990 on the bottom. For the 3/10, we can multiply both sides by 99. I get 990 on the bottom. And for the 2, we would multiply both sides by 990. All right, so let's see what that gives us. Everything's going to be over 990. Okay, in the first fraction, 2 times 990 is 1,980. In the second fraction, 3 times 99 is 297. In the third fraction, 1 times 10 is 10. And the fourth fraction is going to be plus 7. So whatever all that adds up to. Funny, I've done everything without a calculator, but I'm getting out a calculator for the education problem. 1,980. Better make sure that's correct. Yeah. Plus 297 plus 10 plus 7 is equal to 2,294 over 990. So we've successfully written the repeating decimal as a ratio of integers. I did not say in the directions to reduce your final answer, but guess what? We're going to. So we're at 2,294 over 990. 2,294 over 990. First off, both numbers are even, so at the very least I could reduce them by 2. That makes 1,147 on the top, and that should be 495 on the bottom. Sure? Yep. All right, will this reduce any further? Let's see. The top is not divisible by 3. Oh, by the way, what I'm thinking is the denominator was originally 99 times 10. 99 is 9 times 11, 10 is 2 times 5, 9 is 3 times 3. So if I can reduce by anything, it has to be one of those or a product of them, so I'm just shooting for prime numbers. We've already reduced it by 2. Pretty obvious 1147 won't reduce by 5. It won't reduce by 3. You can tell if a number is divisible by 3 if the sum of its digits is divisible by 3. That doesn't work for every number. It only works for 3 and 9. But the sum of these digits is 13. Yes, which is not divisible by 3. So we've already reduced it by 5. It won't reduce by 2. It won't reduce by 5. It won't reduce by any of the 3s. The only other thing it could reduce by is 11. And you could check that manually, although there is a gimmick for seeing if a number is divisible by 11. But this one won't be because you get a remainder of 3. So that means that it's completely reduced, and that should be our ratio. 1,147 over 495. But just to make sure, let's divide it out. 1,147 divided by 495, 2.3171717. We're good to go. Is it a long roundabout way to do it? It is. Is there a gimmicky shortcut? There is. This is a Calculus 2 class, and I want you to understand theory